Hi dear students, welcome back to my second video about transformer on load. And please don't forget to subscribe to my channel and click the notification bell below. Let's start! In transformer on load, once the secondary is loaded, the secondary current I2 is set up. The magnitude and phase of I2, which is the secondary current with respect to the voltage or secondary voltage V2, is determined by the characteristics of the load. So therefore, the characteristics of the load is very important in determining the magnitude and phase of I2 with respect to V2. For example, current I2 is in phase with V2 if the load is non-inductive, or let's say if the load is resistive. While if the load is inductive, secondary current I2 lags the secondary voltage by an angle, and I2 leads the secondary voltage V2 by an angle, denoting that the load is capacitive. To continue, the secondary current sets up its own magnetomotive force, which is equal to N sub 2 times I sub 2, and hence its own flux phi sub 2, which is, take note, in opposition to the main primary flux, which is due to the no-load primary current. The secondary ampere turns and I2 are known as the magnetizing ampere turns. The opposing secondary flux phi sub 2 weakens the primary flux momentarily, and hence the primary back EMF E sub 1 tends to be reduced. For a moment, the primary voltage V1 gains the upper hand over the primary back EMF E sub 1 and hence causes more current to flow in primary. This more current flowing in the primary is the additional primary current called the I sub 2 prime, which is also known as the load component of primary current. This current is antiphase with I sub 2. The additional primary MMF or N1 I sub 2 prime sets up its own flux phi sub 2 prime, which is in opposition to phi sub 2 and is equal to it in magnitude, but it is in the same direction of the primary flux phi. Thus, we have phi sub 2 is equal to phi sub 2 prime, and phi sub 2 is equal to N sub 2 times I sub 2, and phi sub 2 prime is equal to N sub 1 I sub 2 prime, and let us equate them together. Therefore, we have I sub 2 is equal to A I sub 2 prime, where A is equal to N sub 1 all over N sub 2. Hence, when transformer is on load, the primary winding has two currents in it. One is I sub 0, or the no-load primary current, and the other is the additional current in the primary, or the I sub 2 prime, which is antiphase with I sub 2, and K, which is N sub 2 all over N sub 1 times in magnitude. So therefore, the total primary current I sub 1 is the vector sum of I sub 0 or I sub O and I sub 2 prime. So let us study the figure. The figure shows the vector diagrams for a load transformer when load is non-inductive and when it is inductive. In figure 1a, I sub 2 is secondary current in phase with E sub 2. Strictly speaking, it should be V sub 2. It causes primary current I sub 2 prime, which is antiphase with it and equal to it in magnitude. So therefore, the total primary current I sub 1 in the vector sum of I sub 0 and I sub 2 prime and lags behind V sub 1 by an angle of phi sub 1. In figure 1b, it is an example of inductive load. I2 logs E2, actually it is V2 by phi sub 2. Current I sub 2 prime is antiphase with I sub 2 and equal to it in magnitude. The total primary current I sub 1 is the vector sum of I sub 0 and I sub 2 prime and lags behind V1 by an angle of phi sub 1. Figure 1c neglects I sub 0, then phi sub 1 is equal to phi sub 2. Moreover, under this assumption, n sub 1 times I sub 2 prime is equal to n sub 2 times I sub 1 is equal to n sub 1 times I sub 2. So we can conclude that I sub 2 prime all over I sub 2 is equal to I sub 1 all over I sub 2 is equal to n sub 2 all over n sub 1, which is equal to k. So let's have problem number 1. A single-phase transformer with a ratio of 440 volts at the primary and 110 volts at the secondary takes no load current of 5 amperes at 0.2 power factor lagging. If the secondary supplies a current of 120 amperes at a power factor of 0.8 lagging, estimate the current taken by the primary. So we are given in the problem the primary voltage, which is equal to 440 volts, the secondary voltage, which is equal to 110 volts, and the no-load primary current, which is 5 amperes. We are also given the power factor at no load with 0.2 lagging, and the secondary current at 120 amperes. The secondary power factor, which is 0.8 lagging. And then we are required to compute for the current taken by the primary. We all know that power factor is equal to cosine phi, and in our problem, we are provided the value of power factor at no load. And the value of power factor at no load is equal to 0.2. So therefore, power factor at no load, which is equal to 0.2, is equal to cosine phi sub 0. And phi sub 0 is equal to inverse cosine of 0.2, which is equal to 78.46 degrees. The same thing goes with our phi sub 2, wherein phi sub 2 is equal to inverse cosine of 0.8, which is equal to 36.87 degrees. When we subtract phi sub 2 from phi sub 0, we can get the phi sub 1, which is equal to 41.59 degrees. From there, we can compute for I sub 2 prime, which is equal to k I sub 2, where k is equal to v sub 2 all over v sub 1, and v sub 2 is equal to 110 volts all over v sub 1, which is equal to 440 volts. Dividing it, we have 1/4. And the value of our k is 1/4, which is to be multiplied to our secondary current to get the I sub 2 prime. And the value of our I sub 2 is equal to 120. So multiplying 1/4 to 120, we can get the value of I sub 2 prime, which is 30 amperes. To compute for I sub 1, let us use the parallelogram law of vectors, which is equal to the square root of I sub 0 square plus I sub 2 prime square plus 2 times I sub 0 plus I sub 2 prime times cosine phi sub 1. So substituting all the values of I sub 0, I sub 2 prime, and phi sub 1, we have the square root of 5 square plus 30 square plus 2 times 5 times 30 times cosine 41.59 degrees, yielding at 33.90 amperes as our answer for I sub 1. The resultant current could also have been found by resolving I sub 2 prime and I sub 0 into their x and y components. So let's go. So x is equal to 30 cosine 53.13 degrees plus 5 sine 11.54 degrees. If you are wondering where did we get 53.13 degrees and sine 11.54 degrees, we just subtracted 36.87 degrees from 90 degrees as well as 78.46 degrees to be subtracted from 90 degrees. So if we're going to compute for that, we will get the x component as 22.90 amperes. For the y component, we have 30 sine 53.13 degrees plus 5 sine 11.54 degrees. So y component is 25 amperes. So therefore, our I sub 1 is equal to x sub 2 square plus y sub 2 square is equal to square root of 22.90 square plus 25 square, which yields to 33.90 amperes as our answer for I sub 1. A special thanks to the following authors, B.L. Teraja and A.K. Teraja, of the book entitled A Textbook of Electrical Technology as my reference to this video lecture. Thank you everyone, God bless, and see you again next time.